Hello, everybody. I'm Chao, a second-year PhD student at Florida Atlantic University, majored in geosciences. This is my first time to present my research in my life, and the topic is an object graph-based tracking, representation, and analysis for the dynamic behaviors of tidal flats. Tidal flood is the coastal sediment which is alternatively and periodically submerged in water and exposed to the air by the changeable tidal levels. As the land-sea interactions take place, the temperature, salinity, and acidity in the tidal flood region become variable. A unique type of wetland ecosystem is the product of all these factors, which is the homeland of shoreboard fungus, plankton, coastal fish, and so on. Aside from its contribution to biodiversity, tidal flood also plays an important role in carbon preservation and global warming prevention. In addition, the tidal flood has economic benefits. The unvegetated tidal flood all over the world contributes a total of 2.4 trillion international dollar per year at 2011 values. Hence, the dynamic activities of tidal flood have attracted the attention of the researchers from different backgrounds. To cope with the problem, tidal flood dynamic mapping is the essential prerequisite. Prior to the main sections, it is essential to clarify the scope of tidal flood region in this study because it varies from different definitions. In a broad sense, the tidal flood region includes the bare beaches, as well as the vegetated area covered by salt marshes, mangroves, and seagrasses. In a narrow sense, the tidal flood region only includes the unvegetated intertidal zone. This study explicitly aimed at the narrow sense of tidal flood, as the figure shows in this slide. The objective of this study include 1. To verify whether the object-oriented model is capable of life cycle tracking, which is the foundation of event capture. 2. To justify if the graph model provides an enhanced way to represent the life cycles and capture the events of tidal flood. 3. To test if the database has a high performance to store and curate the morphologic attributes of the tidal flood objects throughout each individual life cycle, which is the foundation of further classification for the events of tidal flood. To study the spatial temporal phenomena, it is essential to delineate the cells of dynamic phenomena from the remote sensing images. In particular, we use a method to automatically extract the cells of tidal flood from the satellite images via Google Earth Engine platform. As different types of land cover have different spectral characteristics, the remote sensing derived spectral indices were commonly used for coastal mapping. In this study, we use automated water extraction index, which is AWEI, normalized difference water index, which is NDWI, modified normalized difference water index, which is MNDWI, and normalized difference vegetation index, which is NDVI. As the multiple tiles of images of the same location were acquired by different satellites during different periods, we have sufficient historical records of remote sensing data. For any single pixel's covered area and any one of the above-mentioned indices, multiple values can be calculated from the multiple historical records. Then we use the statistical analysis to filter the multiple calculated values. For each pixel's covered area, we have 54 statistical results. Beside the above-mentioned 54 statistical results, the eTopo1 global relief model and global surface water are also used in this study. The former dataset was developed by NOAA, which gives the land topography and ocean bathymetry data. The latter dataset was developed by European Commission Joint Research Center and Google, which gives the occurrence map of the surface water. These two datasets, combined with the 54 statistical results, formed a dataset of 56 variable identifiers. The random forest is a decision tree-based machine learning algorithm for classification. A method has been developed based on this technology, which uses the above-mentioned 56 variable identifiers and gives an overall accuracy of 82.3% for tidal flood delineation. And this is what we are going to use in this study. At this point, a random selected, pre-computed, and pre-classified sample point dataset has been given, and we randomly divided it into two parts. One, the training dataset, which trains the random forest classifier to make it eligible for classifying pixels based on the 56 variable identifiers. Two, the validation dataset, which is used to access the accuracy of classification results. The geographical phenomenon can be regarded as field-like objects, and object boundaries are defined by the internal attributes. This object-oriented modeling has been applied to many spatial temporal problems. It works for tidal floods issue as well, since every single contiguous tidal flood region can be regarded as an object, and the morphological characteristics of the object may change over time. Therefore, we divided this issue into three hierarchies. One, cell level. It is the satellite image pixels of tidal flood region. The second hierarchy is object. It is the single tidal flood contiguous area with a specific state at a specific moment. The third hierarchy is life cycle. It is the set of tidal flood objects at different moments be linked as a chain based on the relative position relationships. As mentioned in the previous slide, the binary images were generated, in which the pixels with the value of 1 correspond to the tidal flood regions, and the pixels with the value of 0 corresponds to the non-tidal flood regions. In other words, the pixels with the value of 1 refer to the cells in this study. With the extracted tidal flood cells, a component labeling algorithm following 8 neighboring rule was applied to generate the tidal flood objects. For any pair of tidal flood objects, alpha is the object on the previous record, and beta is the object on the latter record, and gamma is the overlapping region between alpha and beta. The overlapping ratio R is formalized as the slide shows, where A alpha, A beta, and A gamma are the areas of alpha, beta, and gamma. The value of R should not be less than 0, which corresponds to no overlapping case, and should not be greater than 2, which corresponds to exactly overlapping case. A threshold is defined to determine whether the two objects can be linked or not. In this study, we use 0.6 as the threshold. As alpha and beta are linked, the predecessor-successor relationship is established, in which alpha is the predecessor and beta is the successor. The predecessor-successor relationship links the objects as chains, which refer to the life cycle in this study. For any object within the generated life cycles, the numbers of predecessors and successors may vary. Several types of basic events were defined based on these two numbers, which were used to classify the dynamic activities of tidal flood. They are appearance, disappearance, splitting, merger, continuation, and recovery. The appearance means when the object has no predecessor. Disappearance means when the object has no successor. Splitting means when the object has 2 or more successors. Merger means when the object has 2 or more predecessors. Continuation means when the predecessor has exactly one successor, and the successor has exactly one predecessor. And the recovery means when two objects have the same predecessor and the same successor. In addition to the above-mentioned basic events, several event types can be further classified by area comparison. The first one is expansion. In case of continuation, if the successor's area is more than 10% larger than the predecessor's area, it is an expansion. Or in vice versa, if the successor's area is more than 10% smaller than the predecessor's, it is defined as contraction. Or otherwise, if the ratio of the successor's area to the predecessor's area is between 90% to 110%, it is defined as stability. And there are two other special cases for merger and split. The first one is in case of merger, you can see we have multiple predecessors, let's say A1, A2, A3 until to AN. And we have only one successor, B. And there are multiple overlapping regions between A and B, which are C1, C2 until Cn. If the area of the largest overlapping region, Ci, is greater than or equal to 60% of the successor's area, it is an annexation. And in case of splitting, we can see we only have one predecessor, which is A, and we have multiple successors B1, B2, B3 until Bn. And we have multiple overlapping regions between A and B, which are C1, C2, C3 until Cn. If the area of the largest overlapping region, which is Ci, is greater than or equal to half of the predecessor's area, it is defined as separation. The figure in this slide demonstrates a tracking result, and we have 4 life cycles. The green one is A, the yellow one is B, the purple one is C, and the pink one is E. By observing the structure of each life cycles, we can find a variety of events happen throughout the 4 life cycles. In discrete mathematics, the graph is defined as a representation of a set of points and how they are joined up, and any metrical properties are irrelevant. Because graph is a concise way to deliver the information, it has been widely used in GIS to represent the evolutionary procedures of the spatial temporal phenomena. In this study, we go further in this direction to explore more about graph algorithms and facilitate the event analysis. In this study, the tidal flat objects are represented by their centroids, and the predecessor-successor relationships are represented by the arrows from the predecessors to the successors. The centroids from the node forms the node side, and the arrows form the edge side, which further constitute the directed graph in 2-dimensional space. For the 4 life cycles shown in the previous slide, their graphs are shown as the figure in this slide. With the generalized graph, the graph algorithms are introduced to help the spatial temporal analysis. The first concept is degree. When the node's in degree is 0, it is an appearance. When the node's out degree is 0, it is defined as disappearance. When the node has 2 or greater out degree, it is a splitting. When the node has 2 or greater in degree, it is a merger. When the successor node has exactly 1 in degree and the predecessor node has exactly 1 out degree, it is a continuation. And you can see a loop in this slide, it is a recovery. Recovery is defined as a group of parallel edges with one net in degree and one net out degree. To date, the spatial temporal database has been used in multiple relevant studies. It may also work for a case study as well. The information generalization of geographic phenomena should not miss any key property contained in the original data. As a result, the above-mentioned generation should meet this requirement. The information has been downgraded from 3-dimensional space to 2-dimensional space. However, the derived graph contains the spatial temporal information and the predecessor-successor relationships, as well as the event types. The database structure of this derived model is illustrated in this figure. First, the life cycle class stores the general information of the specified individual life cycle. Then, the primary properties of the nodes and edges in this individual life cycle are stored in 2 separate classes. Finally, the information of events, which is derived from the nodes and edges, is stored in another class. To verify the method mentioned above, we have implemented a case study. The Landsat 4, 5, 7, and 8 during 1984 to 2018 are used in this study. The study area includes the southwest corner of Florida Peninsula, which belongs to the counties of Collier, Monroe, and Miami-Dade. This area is located within the coverage of the Landsat tiles of Path 15, row 42, Path 15, row 43, and Path 16, row 42. From 1984 to 2018, a total of 2906 tiles of Landsat 4, 5, 7, and 8 images in this area have been pre-processed to surface reflectance tier 1, and all of them are used to delineate the tidal flood regions in this study. A major part of the study area belongs to Everglades National Park. It has sufficient tidal flood region and is regarded as an ideal place to implement the case study. As described in the method part, we get a total of 35 binary images, which are the annual records of the tidal flood cells from 1984 to 2018. To demonstrate the delineation result, we select 6 of them, which are the annual records of 1984, 1991, 1998, 2005, 2012, and 2018, and the map is drawn in the slide. As shown in the map, the tidal flood regions in different years are heavily overlapped, and therefore only some newly deposited tidal flood regions are visible. The most significant area is Sandy Key Basin, which is located off the western portion of the south coast. In this area, the newly deposited tidal flood regions are distributed as layers, in which the earlier deposited layers lie inland and the later deposited layers lie externally. To have a better understanding for the dynamic of tidal flood in the cell level, another bar chart gives the quantitative statistics of tidal flood area from 1984 to 2018. According to the bar chart, the maximum record happened in 1992. The Category 5 Hurricane Andrew may be used to explain the unusual record in that year. According to some previous studies, this hurricane created a substantial amount of sediment deposits along the shallow subtidal coastline in our study area. The graph algorithms provide an effective way to automatically and exhaustively capture the events from a large amount of tidal flood life cycles, which also highlights the object and the life cycle levels could provide more diversified dynamic information than the server level. By counting the numbers of predecessor and successor for each object, we can easily summarize the event types that existed in this life cycle, which include appearance, continuation, splitting, merger, recovery, and disappearance. And the statistical results are shown in the slide. From the upper figure, we can see that aside from the initial year, which is 1984, and the final year, which is 2018, the annual occurrence of appearance is more stable than that of disappearance. In particular, there were 60 disappearances in 2004 and 46 disappearances in 2011, while the mean value of annual occurrence of disappearance is about 28. We can conclude that the year of 2004 and 2011 have unusually more occurrences of disappearance. We can also find a total of 5 peaks in the lower figure that have significantly higher event numbers than the corresponding mean values, which are in the years of 1988, 1996, 2004, 2011, and 2015. Aside from the peak in 2015, the other peaks imply a persistent and stable periodicity of about 7 to 8 years. According to the database structure as mentioned in the previous slide, multiple object internal attributes are stored in the node section in your spatial temporal database, and the area is also included. And the further classified events, which are expansion, contraction, stability, annexation, and separation, are determined by the area changes between the predecessors and successors. Obviously, the database query is a necessary step to find these events. The area query and the thresholding for a large amount of tidal flood life cycles can be conducted via MATLAB, and the quantitative statistics are drawn in this slide. The upper figure indicates that the occurrence of stability is less than occurrences of expansion and contraction, which further reveals the fact that the tidal flood objects tend to have significant area changes rather than keeping steady. However, there were 42 stabilities in 2004 and 31 stabilities in 2000, which are distinctly larger than the mean value of annual stability events. On the other hand, there were 34 contractions and 28 expansions in 2004, and 17 contractions and 24 expansions in 2000, which are less than the event numbers of stability in those 2 years. These comparisons can prove that the fact that the years of 2000 and 2004 have unusually more stability events. From the lower figure, we can find the periods when most separation occurs are the first one is from 1985 to 1993. The second one is from 2001 to 2002. The third one is from 2004 to 2006. The fourth one is from 2008 to 2018. A total of 125 separations happened during these periods, and the periods when most annexation occurred are: the first is from 1994 to 2000. The second period is the year of 2003. The third period is the year of 2007, and the fourth period is from the year of 2011 to 2018. A total of 75 annexations happened during these periods. By comparing the duration of the periods, we could further divide the whole study period into 3 parts. The first period is from 1984 to 2000, in which the trend of separation is stronger than that of annexation. The second period is from the year of 2000 to 2010, in which the duration of the annexation leading and the separation leading periods are short, while the period switch is very frequent. And the third period is from 2010 to 2018, in which the trend of annexation is stronger than that of separation. In addition to the quantitative statistical results, the spatial-temporal characteristics of each type of event can be revealed by plotting the event occurrence places as points on the map. For better reference, the kernel density maps derived from the plotted points are shown in this slide. By looking back at the cell level result, we can find the tidal flood is unevenly distributed along the coast in the study area, which may potentially affect the spatial distribution of each event. This finding is consistent with the figure in this slide, as all types of events share three hotspots, which located around. The first one is the northwestern corner of the study area. The second one is the east end of the coastal area in the Everglades National Park. The third one is the turning point between the west coast and the south coast. The first one locates around the estuary of Shark River Slough, while the second one locates around the estuary of Taylor Slough. Both of them are the principal natural drainages which keep carrying the overland water and mud from the Everglades to the sea. As a consequence, the tidal flood regions are dynamic in both two places. The third hotspot is located around Cape Sable, in which a man-made canal project was carried out in 1922. This project has largely changed the hydrologic environment of the surrounding area. As a result, an active tidal flood region was produced around Cape Sable. As the conclusion, a three-hierarchy model was designed in this study. They are cell, object, and life cycle. The life cycles were conceptualized as graphs, and the graph theoretical terms and spatial-temporal database were used to analyze the dynamic activities and evolutionary events of tidal flood. The future work will be conducted in two aspects. First, we plan to implement the design method in the coastal area of the whole United States, which is tremendously larger than the area in this case study. By implementing the method in a larger area, we expect to verify the universality of the design method and find more regularity of the tidal flood evolutionary dynamics. Second, we plan to implement the design method in the area which is significantly affected by natural or anthropogenic factors like a hurricane or urbanization. We expect to qualitatively and quantitatively describe their destructive power against the tidal flood environments. That's it for all. Thank you for your watching.